Hi, welcome to the breadboard. This is the third video in a set of three featuring the Texas Instruments TIPD215 evaluation module, which is showing off the features and functionality of a DAC8775 industrial digital to analog converter quad channel. So in the first two videos we looked at the features of the board, the register set and configuration of the chip. And in this video now we're going to actually run the evaluation demo software and test the functionality for real, measuring the outputs under voltage mode, current mode, and things like that. And we'll have a look at how accurate it is. We'll put it under 4 to 20 milliamp loops. We'll put it under a voltage outputs, and we'll also vary the supply to it to see whether it has any effect on the output readings. First thing we need to do though is we need to install the evaluation software. Now unfortunately, for the page that's related directly to the board we're using, there are no links to any evaluation software. A little bit of searching actually allowed me to find something that I now do know that will work, and that is from an earlier version. This board here, as you can see, you cannot buy it. It's only for performance validation and testing. The previous version to this could be bought. In fact, I'm not even sure, you may even still be able to buy this one, which is from TI. And what they have here is there's a link to buy it from TI, but there is also some evaluation software that you can download. Now I've already clicked the download link and have it on my tablet. I haven't installed it yet because I wanted to share that experience with you. So let's not waste any time and we'll get this thing installed. So here it is here. We'll just go into the folder. We just run setups. It's only available for Windows, so sorry if you're a Linux or Mac OS user, but that's just the way it is. You can write your own software if you wanted to. There's the data sheets and everything else we looked at in the second video. Here I'm just going to look at the actual provided application because it is quite complete. So let's just finish this. So it looks like this is actually from National Instruments. It's probably a compiled piece of software from their lab view. Anyway, while this is installing, I'm just going to pause and we'll come back once it's done. Okay, so the application is now installed. So I just need to run it. Here we go. So DAC8775 EVM software. Start it up. There we go. So let's just hit continue. Now if you remember what I was saying about the registers, as it said there, you need to do a reset on the chip first. So we'll just hit the reset, and it's done that, and it's read back some parameters from the chip 2, which looks like 800 on the gain, 0 on the offsets. Now if we look here, remember what I said about having to turn things on. If I just try, which I probably as a guess as to what a lot of other folks did, all of my meters right now are reading, getting back to the right mode. Let's just zoom out. Nothing much to look at on the board. You can see how I've connected everything. So let's just zoom out and give you a view on these multimeters. So it's channel 0, 1, 2, and 3. And as you can see with these, they're all reading, okay, so they're all reading pretty much 0 volts. It's 0.00, so 9 millivolts, 8.5 millivolts, 9, and 9. So they're reading fairly consistent offsets. Now if I go into the application and let's just write, so I'll leave it defaults right now of 0 to 5 volts. So if I put in here FFFF and press enter, that should have taken this one up to 5 volts, but as you can see it's done absolutely nothing. Now there's an output enable checkbox here, so let's just turn that on. Well, it did something, but not what we expected. That's 600 millivolts, not the expected 5 volts. So what's wrong with this? Well, the answer is that our boost converter is not turned on. So there is no output. There is no output to actually drive the output. There's no power to drive the output. So we can turn 1 on its own. So we'll just do this and we'll say all enabled. Maybe the reference. There we go. So you have to turn the reference. So just remembering all of the pieces I did. You have to turn the reference on. You have to, if I just turn this back to what it was, you can see the output's gone off again and it's giving weird values. And some of you mentioned that you saw values of about 3 volts-ish. Well, here's why. If your buck boost converter is turned off, but your reference output is turned on, now you can see on this channel, which is the one I'm playing with, I'm getting about -3 volts. That's minus. Let me just turn these probes around so we get the right values. I got them all connected backwards. Okay, so if I now turn the output buck boost back on, and there we have it, 4.9960 volts. So if I change this to say mid-scale, so 7 FFF, you have to input the value in hex. There's 2.5 volts. The main thing is you have to turn on the reference output. That gives a voltage reference for the DACs. You have to turn on the buck boost as well. So you can actually do a command for all of them here, which will turn all of them on, right? And it's done them all at once. Now you can see that 2 of these, this one and this one, have gone to pretty much exactly 0. Let me just zero out the other ones as well. From a value perspective, that one's exactly 0. The third one is doing something a little different for some reason. Oh, it's on hold. That's why there we go. Sorry. So they're all now reading exactly 0 because I've turned on the parts that need to be turned on for the voltage reference and the buck boost converters. I've enabled all of the outputs now and they're still reading 0 very, very nicely. So slew rate, I'm just playing with the first channel right now. So slew rate control here, right? It's 1 least significant bit. My output is currently set, I'll just change these back to where they're supposed to be. My output is set to FFFF, which is 5 volts right now. So if I leave this slew rate control off and I change this to 0, you can see it pretty much instantly goes to 0 on this one here. Now if I enable slew rate control, let me slow down the clock without doing any math and have the step size as 1 LSB. So you can see here that if I now go to 5 volts for that, it's going to take a while. It's going to take a few seconds to get up to that value. You can see now it's actually ramping up. It still hasn't even reached 1 volt yet. Let me just bring there we go. So it's up to 2 volts now. So you can see that's slew rate control for you. Now I've gone worst case conditions here. 4 volts, it's going to get to 5 volts and then it will stop. And there you go. So obviously if I change this to the default, which is way up there, and then I go back to 0 again, it's going to happen much, much quicker. Now, so by default, slew rate is turned off. By default, the buck boost converters are all turned off. By default, the reference output is turned off. So you need to turn all of those on and turn on the output enable in order for anything to work in here. So let me just get rid of slew rate control again for a second. And I'll set this to 5 volts. Now watch, if I just turn output enable off, see it's gone off. So you have to turn on all of those things in order to get anything to work. Now changing ranges, so let's just go from say 0 to 12 volts instead. It automatically clears to 0. Clear select is 0 scale currently, but you can also set it to be mid-scale when you do a clear select. Just bring that back up again. So now if I set this to well, currently it's at 0, so there's 0 to 12. Let me just change this range. Let's just say 0 to 5. And you can see there it went to mid-scale now because that's what I've just changed it to be. 0 to 12 volts is going to go to 6. And if I change it to say 4 to 20 milliamps, it's going to go to, well, actually it's not going to work properly. I'm going to get an alert here because it'll think it's open circuit. So that's gone to 21 volts on the output, and if I actually do a read all, you can see here now that the alarm has come on for this channel because it can't deliver the current. If I actually flip this to current mode, where is it, milliamps, and flip over to milliamps, so it's actually 4 to 20 milliamps, which means we have a 16 milliamp range. So 8 milliamps would be the half range plus a 4 milliamp offset gives us exactly 12 milliamps. So let's just try this. Let's just set this one to full scale, so it should be 20 milliamps. And there we go, very accurate. Set the next one to be 5 volts. And there it is, nice and accurate. We'll set the next one to be plus or minus 12 volts, and 0 is giving us minus 12. So if I put 7 FFF in here, that would be mid-range, which would be very close to 0. And then the last one will set to be 0 to 24 milliamps. But I'm measuring volts, so that will now also bring in, if I reread the alarms, that alarm needs to be cleared, so we'll just clear that. We'll read the alarms. First one stayed clear, the last one is coming back on again because we're in a voltage mode, so we can't read milliamps with that. So let's just flip it to the milliamp range, and there we have 12 milliamps. Perfect. So this looks like it is working very, very nicely. I'm not going to go into a lot more details right now. This is a review of the evaluation module, and really, to be honest, because you can't buy the evaluation module, I'm more interested in what the DAC8775 can do. Now, this software interface here is rather limited in that the only things you can do is what's right on here. So you can see we've already tried the slew rate control. You can adjust the limits for the voltages. So for instance, if you are on a current output, you saw that the output there, the voltage went right up to 20 odd volts on the output. That's because these buck boost converters are controlled by the DAC, and it will ramp it up to try and achieve the outputs. AutoLearn will measure the output impedance and adjust its voltages appropriately. According to the data sheet, you can actually exercise this thing very, very quickly. Let's just bring up the data sheet a second and see what the settling time is, because that's what really, the SPI bus runs very, very quickly. So it would be the settling time for the chip. It's the settling time plus the SPI bus speed that would determine how quickly, or effectively what frequency, if you wanted to do sine wave outputs or something, you could do with this. So let's see if we can find that particular parameter. Oh, here we go, dynamic performance. Voltage output, 15 microseconds, 10 microseconds. So it depends on what you're doing. But it looks like, you know, if you base it on, say, 10 or 15 microseconds, that's quite fast settling time. So as long as you can have a fast SPI bus, you could probably do the math and figure out what that performance is. I'll probably do it and put it in the notes. That's the output voltage settling time. Where's the output current settling time? Current output. So yeah, current output is 10 microseconds as well. So that's pretty good. I think there are some caveats with that, depending on what depending on what your load is and things. So excellent. Anyway, so this is just a review of the evaluation module, or the chip more specifically in this case, because you can't buy the board. You can buy the chip, you can get it as a sample, and there are the bill of materials and Gerber files and things if you wanted to make your own board. What I do like about this is that it is a very good solution to industrial analog sensing and things, where you want to send out a 4 to 20 milliamp loop or 0 to 10 volts, etc., etc. It covers all of the industrial typical voltage and current ranges that you may want to use. But even nicer is that there's a very low count bill of materials, because you don't have to have separate buck boost converters and voltage regulators and everything else, and analog front end for driving the outputs for different configurations, whether it be voltage or current. It's all built into the chip. So while the chip is quite expensive, I think for 1,000 off, it's somewhere around $5 or $6 for the single channel version, and probably about $15 to $20 for the 4-channel version. For a chip that is quite expensive, but if you consider what you're getting for the money, that's not really that bad for an industrial solution that's capable of working with 24 volt supplies, 12 volts supplies, etc. Now, in this configuration with the less than 1 watt operation, this external buck regulator on the input supply is actually bringing it down to 12 volts, which is the optimal voltage for the chip to work on for its internal buck boost converters, etc., etc. So is that essential for a completed system? No, but obviously Texas Instruments deemed it worthwhile to put onto this evaluation module to demonstrate the fact that you could build one of these that consumes less than 1 watt of power, even when all of the outputs are set to 20 milliamps. So maybe I'll do a separate video on a bit of power consumption and everything else. But for now, looking at this, what's the accuracy here? 5, so that's 0.1% on this voltage output. This one is reading, should be on current, so let's put that back to current for a moment. See what we get. Got to give the chip a second to sort itself out. So there's 12 milliamps, so that's well within specification. The last one is on current, and it's supposed to be 12 milliamps, so 0.1, so that's 0.0 something percent accurate, which is really, really good. And the what's this one set to? Plus or minus 12 volts. It's set to mid-range, so that should be 0. So again, for a 24 volt full scale, because it's minus 12 to plus 12, that's not too bad at all, and that's without even using the calibration. So yes, the one limitation I think with this application that comes with it is the fact that it is completely interactive. You can't set up a whole bunch of parameters and hit send. Every time you change any one of these parameters, it will automatically send it out on the USB through the interface chip and onto the DAC. It does contain a simple I/O where you can pick a register to write to and then send a data byte to it or read from a register. So if you wanted to do something manual to try perhaps a configuration that is not supported, then you can do that through this interface. But yeah, so that's simply, you need to use the data sheet in order to understand what you're doing here though. Okay. The main application though here with the block diagram covers all of the basic functionality and has all of the parameters that you can use all laid out very nicely here, and it works just a treat. Unfortunately for this specific board, things like the heart enable is kind of pointless because the heart pin is not made available externally on the board. There may be a way of soldering a pin, a wire or something, very carefully to it, but it's not there to be used at the moment. So you would have to build up maybe a little prototyping board or something like that to do it. Power off conditions, you can actually decide whether it is high impedance current output or a 30 kilo ohm loaded voltage output, or high impedance current and voltage output. This is for maybe if you've got some loads that can will draw power if there's an impedance on the outputs. So you can actually set it to high impedance versus the 30 kilo ohm load. You can actually write to all DACs. Up here it seems like you could write to all of them simultaneously. Just on FFF to everything. Just see what that gives us. So this first one is a 4 to 20 milliamps, so there we are with 20 milliamps. The second one is 0 to 5 volts, so there we are with precisely 5 volts. The third one is plus or minus 12, and we have exactly plus 12. And the fourth one is a 0 to 24 milliamps, and there, as you can see, we've got a nice 24 milliamps, well, 23.995. So I think that the chip, and I haven't done any calibration, the calibration here doesn't seem to be quite having an effect that I thought it would, so I'll have to read up more about that. But the basic functionality of this looks very good. It's out of the gate accuracy certainly meets everything that's published for it, and that's without the soft calibration as well. Quite a nice range, as I said, plus or minus 12 volts. up to 24 milliamps from 0, or even plus and minus 24 milliamps. So that stage that we looked at in the previous video that showed the push-pull for current, well, you can see that it can do minus 20 odd milliamps as well. So that's really cool. Where was it? Oh yeah, there, plus and minus 24 milliamps. So if I go to that one, it's reset to 0, so it's gone to minus 24. So if I go to 0 here, that's what it is at the moment. If I go, because it cleared it, so if I go to 7FFF, it should go to 0 milliamps. And there we have that. And if I go to FFFF, it should go to 24 plus. So there we go. Okay, anyway, that's it for now. Hope you liked it. I will post these screens and things like that so that I can show you in the review what settings you need to turn on. So if you replicate the settings I've got here on this UI, you should be able to get yours up and running as well. Anyway, see you soon. Bye.